welcome to the course Advanced Reaction Engineering. So, in this course we are discussing about the non-isothermal reactor design that is at steady state operations. So, we are discussing. So, today we will discuss about the equilibrium conversions at equilibrium temperature. So, at what temperatures if we operate any reactions, so then what temperature we have to maintain to get higher conversions or maximum conversions or close to the equilibrium conversions. So, that we need to know for any reactions operations in any reactor. So, here let us say any reactions, here we are talking about the reversible reactions, irreversible reactions. So, these are the reactions we will consider, and these reactions may be exothermics or endothermics. So, reversible reactions here, and this is irreversible reactions, and the reactions either one, these reactions may be exothermic, endothermic, and these reactions also exothermic, endothermic, may be either way, it is possibility is there. So, these are the way. So, once the reactions let us say is exothermic reactions is there, if we conduct inside of a reactor that particular reactions, let us say we have a plug flow reactors that we have taken here, if we entering that reacting mixtures at 500 degree centigrade, we are conducting the reactions, and if reaction temperature gradually means if the reactions is exothermic, then what would happen inside of the reaction means reacting mixture temperature will gradually increase. So, once reaction mixture temperature will increase, what would happen? So, then conversions will decrease or maybe byproduct formations is there, means secondary products, secondary reactions or other side reactions would take place. As a result, the overall performance of the reactors would be not good. Okay. So, therefore, we have to think about that, means how we can maintain isothermal temperatures when the reactions is exothermic, endothermic. So, and also to reach the maximum conversions, means for a particular, let us say if we are using one reactor and the reactions is exothermic. So, let us say 40% conversions we can reach by using one reactor, that is the maximum conversion or close to the equilibrium conversions at that particular ranges of temperatures. So, if it is possible, means somehow or some any changes inside of the systems parameter by multiplying using more number of reactors connected in series or any means heat transfer chillers or other things if we use, or heaters or furnace we can use. So, by that way we can reach to the higher conversions by for the same reactions operating the under the same reaction temperature, but here if we use one reactors, let us say 40% conversions we are achieving. So, somehow if here this is reactor 1, this is reactor 2, reactor 3, 3 consecutive reactors we are connecting in series. Here initially reaction was started at 500 degree centigrade, once the product is coming out from the reactor, the temperature is rises to the 800 degree centigrade. What we will do? We will down the temperature of the reacting systems, reach to the 500, again that would be fit to the second reactors. So, in the second reactors conversions will progress and temperature let us say 700 degree centigrade rises to theirs. Then again that reacting mixture we take out from the reactors, down the temperature into 500, again that would be fit to the third reactors. So, in third reactors the reacting mixtures will come out at 570 degree centigrade. So, here we have started with 500 and we are getting 570 degree centigrade, and here we are let us say getting 40% conversions, here we can get 80% conversions. So, for the same reactions, if the reactions is let us say exothermic reactions, if we instead of using one reactors we put 3 reactors connected in series and 2 chillers or heat temperature downing systems if you are connected in series, then we can achieve 80% conversion for the same reactions. So, this would be much more better way. So, this is called, this type of things are called reactor staging with interstage cooling for exothermic reactions. If the reactions is endothermic, then interstage heating is required. So, endothermic reactions is there. So, in that case we have to draw this way, means we have to perform the reactions this way, means we have to pass the feed at that particular temperature. Let us say this is endothermic reactions, temperature will down So, once it would pass here, we are putting catalyst inside of the reactor, feeding the reactant mixtures, reactions will take place here. Once the reactions will progress, then since it is endothermic reactions, reacting mixture temperature would be down. So, then what would have to do? We have to take out the reacting mixtures, in the we have to pass through the furnace, temperature will rise to the 520 degree, 450 to 500 degree centigrade, and that would be fed to the second reactor. R2 is the second reactor. So, then here also we are feed charging catalyst and reacting mixtures, then here conversions will be there, then again temperature will be down, that temperature again will be rise by passing that reacting mixture from the second reactor to the furnace, and it would reach to this temperatures, it would be fed to the third reactors, and by that way we will get product, let us say reaching coming out 500 degree centigrade or 510 degree centigrades, maybe any temperature. So, here if it is let us say 30% conversions, so here by this way we can reach let us say 70% conversions we can reach by interstage cooling. This is interstage heating and this is interstage cooling. So, these are the things, three things we will discuss today. Okay. So, now let us say this is a reversible reactions, and the equilibrium conversions we can express in terms of Xc. So, endothermic reactions, if it is there, the equilibrium conversion increases with increasing temperatures, and that would reach up to the maximum equilibrium conversions or any conversion, that is 100%, that is the 1. Okay. So, up to once x equals to 1, that would reach. Okay. So, here's endothermic reactions, the temperatures and conversions progress is this, means when the reactions is endothermic reactions. So, this way if we increase the temperature of the reacting mixture, conversions that would reach maximum temperature. This would be the temperature profile and equilibrium conversion. And if it is the exothermic reactions, so then it would start with high conversions, and as the reactions is progress, then temperature will increase inside of the reacting mixtures, then conversions will down in case of the exothermic reactions. This is the nature of temperature conversions, equilibrium conversions and temperature profile for exothermic reaction, and this is for endothermic reactions. So, how these are the profiles we can develop for reversible reactions and irreversible reactions also. These are the two things we will discuss. Okay. So, first we will discuss about the reversible reactions and how the temperature equilibrium conversions and temperature is coming for exothermic reactions, that we will discuss. So, let us say this is a first order reactions, the equilibrium conversions and equilibrium constant, that is the Kc, how they are related, this is this. Okay. So, we have to find out the Kc and how the temperature and Kc would vary. Okay. So, temperature and Kc vary, how they are varying, so that we have discussed in your previous class too. So, first what we have to do the material balance in the step 1. This is the red equations for the reversible reactions, since the reactions is reversible. So, we can write minus Ra equals to K into Ca minus Cb by Kc. So, Kc is the equilibrium constant, okay, for this particular reactions. This is reversible reactions. So, this is the rate equations we can write, and K is the further reactions rate constant. And now, here when the systems is at equilibrium, the rate would be 0, okay, minus R equals to 0, means neither forward not backward reactions will progress, but equal rate. So, then minus R would be the 0, and once we put minus R equals to 0 here, and then rearranging these equations, we will get this K E equals to Cb by Ca, we can get from these equations. Okay, after putting R equals to 0, we can get this, and we know Ca equals to this Ca0 minus 1 minus Xc, and concentration of the B, that is the exit of the reactor concentration, that would be Ca0 into Xc. So, both are the things we can substitute here, one will substitute, then these equations we can get. So, these equations how it is coming for this type of reactions. So, it is derivations is given here. So, equilibrium conversions and equilibrium constant for this particular reactions is given by equation 1, and here K is the equilibrium constant for reversible reactions, that we can express this way, that we have discussed in your previous class too. at a particular temperature if you want to know the equilibrium constant. So, we should know the reference temperature equilibrium constant for the reactions, and then heat of reactions R, and this is the reference temperature. This temperature mean Ke at T1, at T1, T1 is the T1 temperatures. If we know Ke value, that some value would be there, and Ke at particular temperatures if you want to know, then T value we should know. So, T value how to find out? From the energy balance equations that we have discussed already for a particular conversion. This temperature we can put here, and then Ke value we can get, and that we can put it here, then Xe value we can come. So, here let us say T1 equals to 298.25 degrees centigrade, that is the standard temperature. So, R value is this, heat of reactions for component A and B is given, difference is given, and K is at 298 Kelvin is given this. So, this Ke value at temperature 298 is given, T1 is the 298, and heat of reactions for this reactions is given, R value is given. So, then this value we have to change, means here one table has been generated, you can see from by equations these equations, means Ke how to find out. First we put 298 here and other components are there, then Ke value we can get. Next T equals to 350 we will put it here, and corresponding Ke value we can find out this. Similarly 400 T equals to 400 we can put it here, corresponding Ke value we can find out. So, like that if we increase the temperature 298 Kelvin to 500 Kelvin, so then Ke value also gradually decrease, okay, for this particular reaction system. So, once Ke value is known at this particular temperature, this Ke we can put it equation 1, equations 1 Ke value here and denominators we can we can put, and by using X equals to Ke 1 plus Ke T. So, this value if we put here and here, so then Xe value we can find out. So, Xe value for this particular point is 1, here is this, and like that it is gradually decreasing. So, equilibrium conversions gradually decreasing. So, now if we plot this temperature and Xe, so this is temperature and this is Xe. So, if we plot Xe versus T, this curve will come, Ke and T if we plot, then this curve will come. Okay. So, this way for exothermic reactions, reversible reactions, these are the two curves we can get. Okay. So, this is from energy balance material balance we have developed. Since rate equations we have started material balance equation, we have developed this. This is called material balance lines or equations, material balance lines. Okay. So, now energy balance, step 2 is the energy balance, means this is the energy balance equations we have discussed adiabatically if the reactions is carried out. So, heat capacity changes for component A and B that if almost equal. So, then differences we can put 0 for simplification. So, these equations we can write this, or either if there is some differences are there, then these equations we can use. If there is no, this is 0, then equation 2 we can use, these equations we can use as a energy balance equation. So, here also denominator part, this part is given, Cp value for component A is known, okay, as Cpi equals to Cpa, that is Cpa is given here, and heat of reactions is given here. So, heat of reaction Cpa value is given, T naught is given, feed inlet temperature T inlet is given. So, this T value we have to vary with X. So, let us say put T equals to 300. So, once put T equals to 300, so then Xe we can get. Similarly, this X equals to Xe, okay, X equals to Xe at 300, that equals to 0. Similarly, if we put temperature let us say 400, T equals to 400, okay. So, then X equals to this, if T equals to 500 let us say, then X equals to this, if T equals to 600, so we will get Xe. So, Xe against T from the energy balance equations also we are getting table 2, and earlier one was the table 1 for material balance, and table 2 is for energy balance table and this is material balance table. Okay. So, now from those two equations we have developed material balance data, energy balance data. Table 1 material balance data, temperature against equilibrium conversions, and from the energy balance temperatures and equilibrium conversion data. So, in the same plots means if we plot this it would be like this. From table 1 it would be like this, and from table 2 Xc and temperature if we plot it would be like this. So, from table 1 data if we plot it would be gives this, and from table 1 data we will getting this. So, both if we plot in the same graph, okay, simultaneously in the x axis temperature, y axis is the equilibrium conversions, then material balance lines would be this is material balance line and this is the energy balance lines. So, both will cross here, okay, that is the point M, that is the called corresponding temperature T and corresponding equilibrium conversions. So, this particular cross point is the steady state temperature, or this is the equilibrium conversion and temperatures. So, that is the maximum temperature or conversions we can get under that operating conditions. Okay. So, that way we can decide what would be the equilibrium conversions and temperatures for this particular reversible reactions by plotting energy balance and material balance lines, and both will cross at this particular point M. So, here that we means operating temperature of the reactors and corresponding equilibrium conversions, maximum conversion that we can reach, that easily we can find out by energy balance lines and material balance lines. Okay. So, here whatever we have discussed means how this from material balance equation is this, energy balance equation is this. So, from this we have developed this. So, this intersections point M is the adiabatic equilibrium conversions and adiabatic equilibrium temperatures, means if the reactions if we conduct inside of the reactors under adiabatic operations. So, then if we maintain this temperature then these conversions will get. Okay. So, reversible reactions we have discussed. So, I think it is clear, means energy balance lines, material balance lines for reversible exothermic reactions. And now, if we consider the reactions which irreversible reactions is going to be, earlier one was the reversible reactions, now we are talking about reversible reactions. Okay. In reversible reactions we can get K1, K2, or you can be Kc, K1 by K2, this way we can get. So, here equilibrium constant and here rate constant this way, means for forward reactions here forward plus backward reactions is there. So, in these reactions we also develop, if these reactions if you operate inside of a reactor and if we operate the reactions under adiabatic operations for irreversible reaction. So, what would be the equilibrium energy balance lines and material balance lines, and what would be the equilibrium conversions for that case, that we will discuss. Okay. So, similarly we are considering irreversible reactions, and we are knowing the, let us see, it is we are conducting in a CST reactors. The design equation is this for the CST reactor, that at the beginnings we have discussed. Next step is the rate law, rate equation is this minus R equals to K into Ca. K we can write this way, that we have discussed. Okay. This is Arrhenius equations we know, small k equals to A into exponential minus E by RT, that is the activation energy. Okay. So, since this is the irreversible reactions, there the energy that would be activation energy. When it is reversible then enthalpy changes is coming. Okay. So, here Ca equals to Ca naught into 1 minus x. So, Ca equals to we can put it here, and this K we can put it here, then rate we can find out. This by step 1 and 2 if we combine and put rate in these equations. So, then these equations if we simplify, so then it is coming x equals to tau k by 1 plus tau k for CSTR reactors, reactions is irreversibles. Then material balance lines are equations is x equals to tau k by 1 plus tau k, tau is the volume by volumetric flow rate, and that is the space time. Okay. These equations also we can write this way. So, here this k equals to this. So, k we can substitute here. So, then it would becomes like this material balance lines, and for C star reactor with heat exchange if there. So, this is the energy balance equations, general energy balance equations. So, if we put shaft work equals to 0 and delta Cp equals to 0, then so only this is present, means heat exchange is there. So, this is not adiabatic operations, we are heat exchange is there, C star reactors with heat exchange under these conditions. So, if we simplify these equations we can get this. Okay. This is for energy balance equation and this is material balance equations. So, if we similarly if we put all components known parameters in these equations and in these equations, and after solving this we can get x and temperatures from these equations, x from material balance equations and x from energy balance equations. So, at different temperature we can put corresponding equilibrium conversion or conversions from the material balance equations we can find out. Similarly, from energy balance equations also at putting different temperature, these temperatures we can put and corresponding Xc value we can get. Okay. So, now from these tables if we plot x axis temperature, y axis conversions. So, from material balance lines it would be like this. Okay. Conversions and temperatures from this table, these data points if we plot it would be like this, and from the energy balance equations this data point and these data points if we plot. So, then it would be like this. This is the energy balance conversion lines and this is material balance lines, both are crossing at this particular point. Okay. So, this would be the corresponding equilibrium temperature and corresponding equilibrium conversions when material balance lines and energy balance lines both cross at that particular points in this figure. So, thus temperature would be corresponding these points, let us say Xc and Te, this particular point M. Okay. So, this way we can say that this is for irreversible reactions, and earlier ones that we have discussed, that was this is for reversible reactions. Okay. This is for reversible reactions, the nature of energy balance and material balance we have discussed, and for when irreversible reactions is there. So, then energy balance and material balance lines, how does it look like to get equilibrium conversions under that conditions or reacting temp means when let us say C star with heat exchange is there. So, the plots we can get and we can get an idea, means what would be the maximum conversions or equilibrium conversion under what temperatures. Okay, that easily we can predict. So, now conversion temperature trajectories or profiles you can say. I said interstage heating or cooling operation is there with the reactors. So, when exothermic reactions is there, so then interstage cooling is required. When it is endothermic reaction, interstate heating is required. Okay. So, here interstage cooling is used for exothermic reversible reactions, that reactions operating adiabatic to achieve high conversions. So, here the diagram is like this, or systems we have to reactor 1, so reactor 2, reactor 3 we have to put, we have to start the reactions are feeding reactor 1s at temperature this, then interstage cooling is there, interstage cooling C1, C2 cooler is there, interstage cooler is there, interstage cooler 2 is there. Okay. So, here cooling would be theirs, and how we can achieve the higher conversions, means this type of arrangement of the multiple reactors and cooling systems for exothermic reactions we can achieve higher conversions. Okay. This purpose of this study is to achieve higher conversions. So, here this is the energy balance lines, this is the material balance lines, that material balance lines we have discussed here. So, material balance lines from the material balance equations we have discussed. So, material balance lines we can draw from the material balance equations, or that equations 1 from the red equations whatever we have developed for exothermic reactions using different temperatures, these curves we can draw. Okay. So, now interstage means now energy balance lines is there. From the energy balance equations we have started with 500 degree centigrade the reactions in the reactor 1s, this is reactor 1. we have started. Then since the reactions is exothermic reactions, so with the progress of the reactions, the temperature of the reacting mixture will increase. See, the reaction mixture temperature will progress or increase gradually like this. See, here conversion was very low, here conversions was very high, 40% let us say, that conversions was that. So, it would reach at this particular temperature. So, once it would reach here, so then we have to take out the reacting mixtures and one cooler is there, we have to down the temperatures again without take out the reactors, the reacting mixtures and down the reactor temperature 500 again. So, here was this much temperature and we are using interstage coolers downing the temperature this, and then again in the second reactor we are feeding at 500 degree centigrade, 500 degree centigrade when conversions was 40% and that reacting mixture we are feeding into the second reactor, this is reactor 2. So, again also exothermic reactions will take place in these reactions reactors 2 and conversions will progress, and at the same time the reaction or reacting mixture temperature also increase and it reach to this. Then again we have to take out all materials from the reactors, we are taking out all reactors and then interstage cooler is there, so we downing the temperature 700 to 500 degree centigrade. So, from this temperature to downing to this temperature 500, again third reactor is there, there we are feeding that reacting mixtures, again exothermic reactions will take place there and the reacting mixture conversions means temperature and conversions would be this. Okay. So, here's that way if we use one reactor 40% conversions we can achieve, but using interstage cooling same reactions by 3 reactors and 2 coolers in series for exothermic reactions we can achieve 90% conversions. Okay. So, by this way 3 interstage coolers 90% conversion can be achieved as compared to the an equilibrium conversion 40% with no interstage coolings. So, if we do not use these are the interstage cooler, if we do not use or this part is if we neglect. So, then only in if we conduct that same reactions inside of a one reactor. So, as per that the equilibrium conversions is like this. So, 40% conversions we can reach, this is the maximum or equilibrium conversions is 40%. So, maximum conversions we can reach 40%. So, but the same reactions by interstage coolings we can achieve higher conversions. Okay. Okay. So, that way we can achieve 90% conversions. This is the beauty of this way, means temperature and conversion trajectories with interstage cooling. Okay. Similarly, for endothermic reactions, when we talk about endothermic reactions and interstage heating is required, exothermic reaction interstage cooling is required, and when endothermic reactions and reversible reactions we are conducting, this is a reversible reactions you can see. In these reactions if we conduct in a reactor, so then reactions is endothermic, with progress of the conversions the temperature of the reacting mixtures will decrease gradually. So, then heating is required, means to achieve higher conversions, means equilibrium conversions let us say it is 30% conversions, but interstage heatings if you want to get 60% conversions, that is good. So, how that is possible? Similarly, interstage 3 reactors here you can see, this is the reactor 1, 2, 3 reactors we have taken in series, and see here inside reactor 1 feed is at 520 degree centigrade we are feeding, at the same time catalyst also is charging here, so reactions will take place at 520 degree centigrade. Since the reactions is endothermic reactions, so therefore, the reacting mixture temperatures endothermic reactions I said the reactions is endothermic. So, temperature 500 to 450 degree, means inside of the reacting mixture temperature will down. So, once the reacting mixture temperature will down, so the reactions conversions will decrease, okay, rate will decrease. So, then what would happens, again take out the samples or the reacting mixture and pass through the furnace 1 and heated up, and by interstage heatings its temperature would reach 520. So, then again it would be fit into the second reactors, and by that way again also the same catalyst we can charge here and another catalyst we can charge here, reactions will take place here, and then again temperature would be fall here. So, then that mixture again take out and put pass through the furnace 3 A2 and reach the temperature 520, and then the reacting mixture should be fed to the reactor 3, and here also we are charging catalyst, and after that we will get higher conversions, whatever the product will come out. Here let us say 30% conversion, and here conversions that we are getting 60% conversion by this way. Okay. So, here if we see this diagram endothermic reactions. So, we have started with 520 degree centigrade fed, and once reactions is progress, this is the material balance lines. Okay. So, now energy balance line, this is energy balance lines. Here we have started, and once the reactions is progress, inside of the reacting mixture temperature will down, since the reaction is endothermic. So, with the progress of the reactions, conversion gradually increase, temperature of the reacting mixtures will down. So, then it would move this way, energy balance line. Once it would reach here, take out the samples, stop the reactions, the samples will take out from the reactor, reaction has stopped, then it would be passed to the furnace to reach this temperature. So, again we increase the temperature by putting furnace, here furnace 1, here furnace 2. So, this way again if we heat it up, and in the second reactors, reactor 1, this is reactor 2 again if we start, then reactions conversions will progress like this, and temperature again will fall. So, that way, and again that reacting mixtures we have to take out, and you have to pass in the second furnace, again temperature will reach to the 520, and then in the third reactors reacting mixtures will reach, and reactions will take place in presence of catalyst, then conversions would be theirs. So, by that way this the energy balance lines, this is energy balance lines for reactor 3, for reactor 3 this is the energy balance lines. So, it would reach here, by that way you can see this is the equilibrium conversions here, this is very good equilibrium conversions, here equilibrium conversion, this is the equilibrium conversion, that may be 30%, let us say we can reach 60% or 90, let us say this is 60% conversions. Okay. So, we can reach like this way 60% conversions or higher conversions we can achieve. Okay. So, I think it is clear to you, means when interstage heating is required, when interstage cooling is required, and why it is required to get higher conversions, and how that we can achieve, means multiple number of reactors with interstage heating or cooling arrangement is there, then we can achieve higher equilibrium conversions for that particular reactions. If there is conversion is very low for that particular reactions. So, means if we use one reactors we can reach of course in the equilibrium conversions, but the equilibrium conversion is very low. So, once we put multiple reactors in series and interstage heating or cooling, then we can achieve higher conversions. Okay, that two things we have discussed, and another things is reversible and irreversible reactions, conversion temperature profiles. For reversible reactions we have studied, and irreversible reactions we have studied, and reactor stagings with interstage heating and cooling we have studied. So, these are the three things we have studied. So, I think it is now clear to you. Thank you. So, today is up to this. Okay. So, next day we will discuss something different or something else. Okay. Thank you.